This is Math 226, Vector Calculus. And we are doing section 13.2 on vectors in three-dimensional space. So let's take a look at the book. Here it is. Vectors in three dimensions. So again, this should be very familiar. For one thing, we live in three-dimensional space, so there's nothing unusual here. So we have three dimensions. There are the usual x and y dimensions. So you have the xy plane. And in section 13.1, we considered vectors in two dimensions. Now we add a third dimension. So in addition to the x-axis and the y-axis, which are perpendicular and form a plane, perpendicular to both of them is the z-axis. And once you have your x and y axes and you draw a z-axis, the question is, which direction in the z-axis should be the positive direction and which should be the negative direction? So on your x-axis, you choose one ray to be the positive part of the x-axis, and you choose another ray on the y-axis to be the positive part of the y-axis. And if you can imagine putting your hand just as it's drawn here in the picture, but it's very important that your right hand. If you use your left hand, everything is backwards and wrong. Because this is what is called the right hand rule. You imagine putting your right hand around the z-axis perpendicular to the xy plane. And in fact, if you like closing your hand around the z-axis and your right thumb is pointing in the positive direction on the z-axis. So if you usually draw the three-dimensional space like this x and this y, z is always up. But no matter how you might orient the x and the y axes and choose which half of them is the positive half, the right-hand rule gives you the positive direction in the z-axis, and the other direction is the negative axis. And if you look at the x, y, z three-dimensional space, there are what are called the coordinate planes. For example, if you take z equal to 0, you just have the plane through the x and y axes. That's the xy plane. If you think of y equal to 0 and you take the plane through the x and z axes, that's this vertical plane. That's the xz plane. And if you take x equal to 0, you're looking at all the points with coordinates in this yz plane. So you have three coordinate axes determined by three coordinate planes determined by the axes. And you actually have also, if you look at this picture very carefully, 8 what are called octants. You remember in the xy plane, without the z-axis, just the xy plane, you have 4 quadrants, 1, 2, 3, and 4. Here, x and y are both positive. Here, x is negative and y is positive. Here, x and y are both negative. Here, x is positive and y is negative. There are 4 quadrants in the plane, but when you look at three-dimensional space, you actually have 8 octants. For example, you have the positive octant where x, y, and z are all positive. And for every choice of plus or minus signs for x, y, and z, and there are 8 choices, you get a different octant. It's very hard to draw something three-dimensional in a two-dimensional piece of paper, but you can picture that, what it is. Just as we assign coordinates to a point in the plane, 2 coordinates, we assign 3 coordinates to a point in three-dimensional space. So for example, by the point with coordinates 3, 4, 5, here's a picture of it. You go 3 units in the x direction, 4 units in the y direction, and 5 units in the z direction. And this is the point with coordinates 3, 4, 5. If you look at the point -2, -3, 5, you go, here we are, 2 units in the negative x direction, 3 units in the negative y direction, and 5 units in the positive z direction, and you end up over there. So you associate coordinates to every point in three-dimensional space. That's kind of clear. And you can also write down the equations for very simple planes. For example, if you look at all the points in the plane where z is equal to 0, then you're just in the xy plane. So z equals 0, this is the xy plane, the green, pale green down here. If you look at all the points with z equals 3, that's a parallel plane. That's a plane parallel to the xy plane, but raised 3 units higher. If you look at all the points where y is equal to 4, that's a plane parallel to the xz plane. The xz plane is all the points with y equals 0. If you look at all the points with x equals 0, that's the yz plane. And you need to spend a little bit of time looking at the pictures to understand the very simple geometry that we're discussing here. But it's like many things, it's only simple after you understand it, and I've worked a little bit to make sure you get to understand it. But it really is simple geometry. Just as we had a nice formula for the distance between 2 points in two-dimensional space, we have the analogous formula for the distance between 2 points in three-dimensional space. So if you have the point P with coordinates x1, y1, z1, and the point Q with coordinates x2, y2, z2, the distance between them, and this is really just the generalization of the Pythagorean theorem from two-dimensional space to three-dimensional space. You take the square root of the sum of the squares of the differences of coordinates. That's the distance between 2 points in space. And if you want the midpoint, so if you take the point P and the point Q and you draw the vector between them, or the line segment between them, you get the midpoint, the halfway point on that line, by just taking the average of the x, y, and z coordinates. So the midpoint between the points P and Q, here's a picture. You take the average of the x coordinates, x1 plus x2 over 2, the average of the y coordinates, y1 plus y2 over 2, and the average of the z coordinates, z1 plus z2 over 2. And that's the midpoint. Just the way we have circles in the plane, we have spheres in three-dimensional space. So a sphere is a set of all points. So remember, a circle is all points that are a certain fixed distance from a point in the plane. A sphere is a set of all points that are a certain fixed distance, r, from a point in three-dimensional space. And r is called the radius of the sphere. And the point, let's say the point is ABC, is the center of the sphere. So the sphere is just the shell is all points exactly distance r from the center. The ball is a solid object. It's all points which are distance r or less from the point ABC. And we can see the picture right here. So the sphere is the surface of the ball, and the ball is the solid ball. It's the surface and everything inside. Exactly the same as in the plane, where you have the circle and then the disk, which is the circle and everything inside the circle. So in three-dimensional space, we have spheres and we have balls. And if you want, for example, to find the equation of a sphere, it could be described like this. Suppose you have the points here, P is 1, minus 2, 5, and Q is 3, 4, minus 6. So there's a line segment from P to Q, and we want to find the equation of the sphere for which this line segment's the diameter. Now, if this line segment's the diameter, the midpoint is the center of the sphere. So how do you find the midpoint between P and Q? Well, you take the average of the x, y, and z coordinates. So for P, the x coordinate is 1. For Q, the x coordinate is 3. The average of 1 and 3 is 1 plus 3 over 2, or 2. For the y coordinates, minus 2 and 4, the average is minus 2 plus 4 over 2, which is 1. And the average of the z coordinates, 5 and -6, is -1 over 2, or -1/2. So this will be the center of the sphere. And what will be the radius of the sphere? Well, the diameter of the sphere is the distance from P to Q. So if you use our formula that the distance is the square root of the sum of the squares of the differences of the x, y, and z coordinates, you get this number, square root of 161. Well, square root of 161. That's the diameter, so the radius is half of that. So we have a sphere whose radius is a half square root of 161. This is the center. So the equation of the sphere is x minus 2 squared, y minus 1 squared, z minus -1/2, which is z plus 1/2 squared, is the radius squared, which is 161 over 4. So that's the simplest geometry we have of spheres and balls in three-dimensional space. Again, a vector in three-dimensional space is just like a vector in two-dimensional space, except there's a third coordinate or a third component. So if we write a vector with coordinates v1, v2, v3, that is the arrow, the vector, which has its tail at the origin and its head at this point in three-dimensional space. And if you want the vector from P to Q, P and Q are two different points, neither of which has to be the origin, but they have coordinates x1, y1, z1, and x2, y2, z2. You look at the difference of the x, y, and z coordinates, and those are the coordinates of the vector from P to Q. So we have the same operations on vectors in 3 space as we do in 2 space. In 2 space, we could add vectors, subtract vectors, and multiply a vector by a scalar. In 3-dimensional space, we can do the same thing. And again, just as you see here, this is the definition of the operations. If you take vectors u and v, the sum u plus v is obtained by just taking the sum of the coordinates pairwise. The difference of the two vectors is the difference of the coordinates pairwise. And you multiply a vector by a scalar c by multiplying each coordinate by c. So here's the vector v. If you multiply it by c positive, you stretch it by a factor of c, pointing in the same direction. If you multiply by c negative, you multiply the length by c, and the vector is pointing in the opposite direction. And the exercises are exactly the same as for vectors in three-dimensional space. The length of the vector, well, you have the vector from P to Q. These are the coordinates. The length of the vector, again, is just the sum of the squares of the differences of the coordinates. It's the distance from the point P to the point Q. In 3 space, we have now 3 unit coordinate vectors. I is a unit vector in the x direction, so its coordinates are 1, 0, 0. J is a unit vector in the y direction, so its coordinates are 0, 1, 0. And k is a unit vector in the z direction, so its coordinates are 0, 0, 1. So those are the 3 unit coordinate vectors. And ijk is standard notation. And again, if you've taken, for example, some physics, you will be very familiar with this. And that's all there is to it. There are 1 or 2 examples that we'll go over when we're doing homework problems. But that is vectors in 3-dimensional space. So that's it.